Okay, thank you for the introduction. I'm presenting a text on wireless coexistence. My name is Jiska Classen, and this is joint work with Francesco Gringoli, Michael Hermann, and Matthias, Hollick. So in a wireless coexistence attack, the idea is you have different wireless chips. And for example, now the Bluetooth chip could try to attack the Wi-Fi chip on the same device. And this is possible, like if you look onto a modern phone of any vendor, you have shared components within radios or connections in between radios. So even though they're like all different technologies and separate chips, some of this is shared and could be exploited. So in this paper, for example, we show that the Bluetooth chip can get code execution on the Wi-Fi component, but also there's other possibilities. So for example, last week at WiSec, I presented a paper that shows that the Bluetooth, NFC, and ultra wideband chip stay on when the phone is powered off, and they also are interconnected. And of course, vendors don't do this because they say, hey, we want a new attack surface, but the motivation behind this is like mainly performance. So in a wireless medium, you have, for example, Wi-Fi and Bluetooth. They both transmit on 2.4 gigahertz, and also some LTE carriers are on the same frequency. And because of this, they need to schedule packets. So you cannot transmit two packets on the same frequency of Wi-Fi and Bluetooth, and also not receive. So you have to talk to each other kind of to coordinate this. And because it's a shared medium anyway, you can already minimize hardware costs, because you can say, okay, we now share also the 2.4 gigahertz antenna. This saves you some cost. You can also have memory components in this transmission chain that you share. It just makes it cheaper. And then another motivation can be power saving. So for example, some protocols have like Bluetooth and ultra wideband, and then the Bluetooth chip can just make ultra wideband when it is needed, so that you just save power in the whole protocol. And sometimes there are new features. So the work that I presented last week at WiSec was, I think, motivated by the digital car key 3.0, and the digital car key uses Bluetooth and ultra wideband, and it's also connected to the NFC secure element. So that's like all different motivations to have these hardwired connections in between those chips. So many manufacturers have these connections, but now the question is like, can we also exploit this feature? And of course, the answer is yes, otherwise I wouldn't be here. So I mainly looked into Broadcom and Cypress chips. So that's a very big manufacturer. Like their chips are used in all iPhones up to the most recent iPhone, in many Samsung phones, in the Raspberry Pi. So you can find those chips really everywhere, and I think every one of you has like a device with one of those chips. And then we also, for comparison, got some chips from Silicon Labs, so that's not as big as a manufacturer, but still a good market share. And they have a coexistence development kit, which was very nice for analysis, so, and also had some documentation. And we found that inter-chip attacks are possible. So we found like denial of service, like one chip tells the other, no, I'm transmitting, please never transmit. This is possible for all the manufacturers. And because they coordinate packet transmission and other information, you can also leak some information between those chips. And we found code execution, which we only confirmed for the Broadcom and Cypress chips, but who knows, maybe there's other vendors with like similar vulnerabilities. And because of limited time, I'm now only going to show you like 2 of those attacks, but you can find more attacks in the paper. So previously, I've been working a lot on Bluetooth security, and when developing a framework for Bluetooth chip patching, I found already a vulnerability in there, and then a student I supervised developed a fuzzer with emulation, and he found even more remote code execution vulnerabilities on Bluetooth chips. So we thought like it's a good idea to like start with Bluetooth as the entry point to a system. Now the thing is like Bluetooth is a bit limited. Like even if you would manage to escalate into the operating system, which you are not if you're on the chip, it's sandboxed. And then the escalation to the operating system is also complex because it's connected via UART. That's a very limited serial protocol, so probably programmers will not make that many mistakes in the driver. But Bluetooth is interesting, like it's warmable. You can initiate a connection and receive a connection, so you could build a Bluetooth worm, but then this worm is like unstoppable, like it has no internet back channel, so yeah, I don't know, but it has interesting properties. Now if you look into Wi-Fi, I mean, on the operating system level it's also sandboxed, but it's connected via PCI Express, and that's a way more powerful interface, also meaning that it's more likely that programmers make mistakes in here, and Wi-Fi allows internet access. It also, like on a chip level, without any escalation, already knows the network key of the Wi-Fi that you're currently connected to decrypt and encrypt packets. So it's just two different technologies, and finding something that kind of combines the technical capabilities here is really an interesting capability in the end. So now I'm going to talk about two attacks that affect Broadcom and Cypress coexistence. And the first one is on a hardwired interface, which is a serial interface between the chips. It's called the Enhanced Coexistence Interface. For this, you can already look a bit into the data sheets where it's explained briefly what it does. So the idea of this Enhanced Coexistence Interface is you have a serial connection between Wi-Fi and Bluetooth, and you coordinate when they send a packet. And this is really essential. So let's say I have a Bluetooth headset and I'm streaming a YouTube video, something like that. I want just to listen to it. What you would see without the coexistence interface, so if you disable it, like the video would buffer, and then you can hear it like for a few seconds, and then like again it buffers, and it's just really annoying. And this interface enables you to do both at the same time with a high throughput without packets getting lost. Now, this interface has some control registers, and simply writing invalid values to the control registers crashes this interface, and also from Bluetooth you can crash the Wi-Fi chip, so the Wi-Fi chip really restarts. And on the interface between the chips, when you have a serial analyzer and or logic analyzer and look like into this protocol, you can even see that there is a voltage drop in between, so that's really weird. And because of this hardware behavior, then the Wi-Fi chip does not start again like correctly. So the Wi-Fi chip is just restarting, or the operating system attempts to restart the Wi-Fi chip without any success. And on many operating systems, so also Samsung phones, but also macOS, iOS, we saw that this can cause the operating system to restart because it just times out on the PCI Express channel. So that's a demonstration here. So on the left-hand side, I write to a configuration register. That was very fast, but you see it again. On the left-hand side, I do this. And then on the right-hand side, you can first see Wi-Fi stops to work. So that's the ping that stops on the right-hand side. And then after a few moments, the operating system restarts. So this is still only denial of service, but a very powerful one because it escalates into the operating system. Now I have a second example, which is even more interesting because we can even get code execution between the chips. So initially I thought, hey, there's this serial protocol. Now we can try to look for side channels, extract information and stuff, and I spent a lot of time on this just to see like how powerful is this interface for any form of exfiltration. But in the end, it turns out there's like even more. So there's not much documentation and leaked data sheets. So there's like some drawings similar to this, and also not in all versions. But there was this one version of a data sheet where they mentioned something that's called like Wlearn RAM sharing. You can see it's only in one direction. It's not documented except from like this one figure, but a lot of reverse engineering later I found out like how to use this feature. So actually on the left-hand side you can see I'm writing to yet another special address which is mapped from Bluetooth to Wi-Fi. So yeah, you can see my mouse pointer when I'm moving. So here I'm writing a branch instruction to an address like on Bluetooth, and then like to a very high address, and this is mapped to Wi-Fi, and then a moment later like Wi-Fi is restarting and it's crashing at this address. So this shows that we really can control the code flow and the code that is executed in Wi-Fi, which is really an interesting property. And of course, this is something, I showed you that this works for Cypress and Broadcom, but it's a more generic issue. Like, if you look into data sheets, all major vendors, they mention that they have a coexistence interface. Like, of course, they are not described in a lot of detail, but they mention we have interfaces for coexistence. And we found like the same, like denial of service, information leakage stuff, it's possible for Silicon Labs chips. There is one restriction, so some chips, they don't separate those technologies. Like, for example, you might have one chip that has multiple wireless technologies running all on one core. Then this type of attack is kind of possible by design, but still it means like on the operating system level, there might still be some leakage or something, or you still have like this powerful property that the sandboxing of the operating system will not really separate Wi-Fi and Bluetooth because it's attackable on a chip level. And with this, I'm going to conclude my talk. So first of all, the security impact is that like all wireless chips, they are now forming a complex subsystem. And so exploitation of one chip can now lead to exploitation of this whole subsystem if there are hardwired connections. And these hardwired connections also mean that the attacks cannot be prevented by the operating system. Like, it's a serial connection between two chips. It never passes the operating system layer, and it's hard to stop this attack. And this also means that if the operating system is sandboxing, Wi-Fi, Bluetooth, whatsoever, this sandboxing is not effective on the hardware layer anymore. So we really have to rethink wireless attacks more on attacks of like the whole wireless subsystem rather than one single chip, and it's also changing the threat model in the wireless world here. All right, and with this, let's go to the Q&A.
All right, let's thank our speaker. Before our first question gets up, I just want to ask you something really quickly.
Yes.
This is very, very cool work. Have you thought about, I mean, you've mentioned that we need to rethink what security looks like, but how do you do this isolation? I mean, what does it look like other than separating them onto two separate chips?
Yeah, so I think when this was designed, like the vendors did not really think about like security, but more performance, and this is what caused it. I think, so we have not seen any validated checks. Like, for example, the vendor could now try to check if, I don't know, Bluetooth claims all resources, is this valid or not? This can be implemented on a protocol level, so they could implement protocol checks here, assuming that now chips are attacking each other. Something that cannot be fixed easily in the current generation of chips is, of course, like a shared memory component. You cannot really remove this, but long term you could think of like, is this needed? Can we separate it?
I guess I had a very similar question as Patrick, but my thoughts are that maybe at the OS level, would it be possible to, fundamentally virtualize the transmission of data across different wireless channels, and could that have an impact on, improving the security?
By virtualizing, you mean like, I mean, it's already going through separate drivers, separate levels, so it's very separate on the operating system level already. I'm not sure if that would help. So adding another layer of abstraction, I don't think so that it would help. Like, the hardware is still connected. But yeah, operating system, you have like the Bluetooth framework, which is used by the application. Then the framework is using the driver on user space, which is then talking to the kernel, which is then actually talking to the hardware. So it's already having a lot of components that are somehow separate.
Yeah, I guess that does, answer my question.
Yes.
But yeah, thank you.
All right, any more questions? Okay, let's thank our speaker again.
Thank you.